We start up again with finite differences. So finite difference is the first method people used to solve differential equations numerically. So it's a rather straightforward, easy concept. We will turn later on to finite volume, which is a little bit more complex. Finite difference, very easy. It's based on the Taylor series. So you have a function, what do I call it? Taylor series, you will have a function u of x plus delta x. And then you say this is roughly the same as, and then you have u of x, delta x multiplied with u derivative of x plus delta x squared half u double, and so on and so forth. You can go the other way. Negative x direction. If you have the solution at point x, what is the solution next to it at a distance delta x away? You get the exact same recipe, but now every other term will have negative. Minus delta x, first order derivative, then plus again, delta x squared half, double, and then minus, and then higher order terms. So from these two series, you can sort of construct whatever you want. Last time we used a forward Euler scheme in time. So that's actually just isolating this guy from the first recipe. What do you get? You say u derivative at the position x then equal this guy, u x plus delta x minus u of x divided by the distance you are walking, and then you will then have plus terms of order. What will the order be? Well, this one is second order accurate, but you have divided with delta x across the entire equation, so this will be of order delta x. So there you have a forward discretization, first order scheme. And of course, if delta x is small enough, it can be fairly accurate, but it's not that impressive. So of course this is the first one that you try, but first order, remember. This is what we did with time for the Navier-Stokes when we looked at the projection method last time. And you can do the same now with the second one. Isolate u derivative here. It will be the exact same recipe, but it will be negative here, and then actually a negative there as well. So that's called a backward difference, not forward difference. You can play around with these as much as you like. Another one you should be familiar with. If you take a double derivative, so you sort of add these two together, a little bit algebra, you will find this one, double derivative in the position of x equal, it will then be something like this, u x plus delta x minus 2 times center point u of x plus u x minus delta x, and then divided by delta x squared. This is actually a second order recipe. You can also use a higher order density for the first order, That would be better. Not a forward, not a backward. If you do it like this, u derivative of x. That's just the first line minus the second one, and then a little algebra. U x plus delta x minus u of x minus delta x divided by 2 times delta x. This is second order accurate. You find a lot of these stencils in numerical books. So, but here you have the most important that we are going to use. First one, it's a forward, and the other two we call them central space because you see they are symmetrical around the point x. Take one on each side to create a derivative. And here you take one to the left, one to the right, and 2 of the center point to create a double derivative. So this is finite difference for you. So now you just take your partial differential equation and take all your derivatives, second derivatives, and you replace it with these stencils, these algebraic equations, and then we have a numerical problem. Let us look at an example. Any questions to this? It's okay. You should have seen it before, I hope. At least something of it. Example. We take a simple Laplace equation. That was the double derivative equal to 0, which is an elliptic equation. So here we have x and y, and then I have a square region in space, and inside this region I want to solve the Laplace equation, say for the temperature. Laplace square of T equal to 0. So this is my problem. Then we need some boundary conditions. Here I have chosen, let's see, the top wall here, he is hot. Temperature equals 1. The right wall, he is cold. So those two we call Dirichlet condition. You give the numbers directly. The 2 other walls, there we use a Neumann condition, derivative equal to 0. So meaning they are insulated or something. So here, x derivative is 0, and down here, dt dy equal to 0. This is the problem. Find a solution. Find a numerical solution. How do we do this? Then we use the double derivative. We have the recipe here. So we just have to make some derivatives of this temperature. Well, first of all, we have to sort of split up our domain with a mesh. So here we make a mesh, something like this. And we want to find the solution, say now in the corners of these small meshes, small rectangles. And I will now use, just to confuse you, instead of x and y, we will use I and j as indexes. So here and here. We are talking at say an arbitrary point here somewhere. Here you'll have T, I, J. So we have a discrete representation of a continuous function. And how will our equation look like? Double derivative with respect to both x and y is now roughly the same as. And then we say t. First we need the derivative. Here it was in the x direction, but now I'm using the indexes. I will go from say 1, 2 up to n or something like that. So here you need plus delta x will now be represented with just plus 1. So that's the neighbor point, right neighbor point to the center point, which is just called, oops, I need comma j as well, j, and finally I minus 1j, and then divided by delta x squared. And then you do the same in the y direction. J plus 1, 2 times ij plus ij minus 1 divided by delta y square plus order delta square, second order accurate. And now we make it simple. I have a square in space. I use the same number of points in both directions. So I have an n by n matrix here. Also, I said delta x equals delta y. That makes things very easy indeed. Because on the right hand side of this equation it actually reads equal to 0. So instead of delta x and delta y, we do the following. Then you see our recipe will be much easier. We will have t I plus 1j, t I minus 1j, t I j plus 1, ij minus 1, and finally 4 times of the center point ij equal to 0. That will be my recipe, my algebraic equation for any arbitrary point ij. So I just need to solve this equation, or these equations you might say, because if it's 10 by 10 grid you have here, you have 100 algebraic equations which must be solved together. They are of course strongly coupled. So yes, you could of course here set up a matrix, solve it using a direct method, yes, that's possible. But in general, that's expensive. You will blow the memory for any big problems. So no, we are using the Newton-Raphson, the modified Newton-Raphson on this problem. So this 0, this is actually now my function fij that I had last lecture. This is the function I want to have to be 0 for all i's and j's. So what was the recipe? Well, the recipe should be something like this. My new Tij equals the old one, and then it was minus omega, and then comes my Fij. That is the entire expression here, divided by the derivative of my function f with respect to the unknown that I have sort of focused on, the center point. So take the derivative of this function with respect to Tij, that's minus 4. That's it. That's my recipe. For the boundaries, Well, the top wall, these values, they are given, and the right values are also given, so these are known. No problem with these guys, that was the Dirichlet condition. But what about the left boundary and also the bottom boundary? There we had Neumann condition, derivative equal to 0. How do we do that? That's a little tricky, isn't it? But let's see now. Here is number 1. And here I have some cells. And these are unknowns. These are lying on the boundary. That's number 1. What I want is to have this one equal to 0 at this location. This was on the boundary. Index number 1 here. The x position 0 if you like, but the index number 1. I want this one to be 0. Okay, then we use this stencil. I create a derivative using the values to the right. That is t x number 2 for all j minus, and then I have something in here inside the wall. That's a neat trick. You use ghost cells inside the wall. They're not real, but very convenient if you want to use them for boundary conditions. So I invent sort of a fictitious value inside the wall. I call him T0j divided by 2 delta x or 2 h's, was it now? Like that. Well, if he is supposed to be 0, you can multiply with 2h, and then you say these two has to be equal, meaning this strange value I have inside the wall, this one, number 0, equals number 2, the one we have here. So that's very easy. When you do the programming now, you won't set up space in memory for these fictitious values. You don't need them, because what you then should do much better is to take your stencil, your recipe, and you create a special version for the boundary value here along I equals 1. I equals 1, then you see you address I minus 1 here. That should be number 0. So he will then be replaced with number 2 instead. So for, we can write it like this. If I equals 1, what will the recipe be? This one, T0, doesn't exist, but we know him to be equal number 2, which we have here as well. So we'll have 2 times of T2j plus, and then what else do we have? T1 comma j plus 1, T1 comma j minus 1, and then minus 4 times T1j equal to 0. So there you have your special version of your stencil. And then you do the same at the bottom. So that's the correct way to do it. It's possible to use fixture cells and then update them later. That's not so efficient. It will be a little bit slower. But okay, let's see how the program looks. Any questions here now before we start the demonstration? It's okay? Okie doke. Let's see if we can make it work here. Screen. Right. how does the solution look, do you think? This one is 1, this one is 0, and here derivative equal to 0. So it's going to be a rather curved, strange region here, of the distribution of temperature. Corner point here is of course a question. Is it 1 or 0 or 1/2? I don't know. Really doesn't matter, it's just cosmetics. But what we can say is that the solution should be symmetric around this diagonal, and the value down here should then be 1/2. So let's see if we can make it. Here, cute little MATLAB demonstration program. I can put this one out on the home page if you like, if you want to play around with it. So I just set up 50 by 50 cells. This over-relaxation parameter, omega, is set to be 1 initially, and then start with zeros. And then we see what happens. So here you have the initial solution. So temperature is 0 all the way in the domain, and then all of a sudden 1 at the top wall. Then we start to iterate. And now remember, for every iteration you will have to update all, 50 by 50 unknowns. So but you see, it's very, very slow indeed. Extremely slow actually. So this, no, not so impressive. He's going to get there in the end, but it's going to take forever. This point here hasn't even started to move. He should be up to 1/2. So this is boring. Now let's try to speed things up a bit. Let's see, why didn't he show? Who cares? We increase this omega factor 1.5. See if it helps. That helps a little bit. This Fij, he should then be 0 actually. So no, still not a symmetric solution, so let's try to increase him further. Let's try 2.5. A very, very bad idea. Let's try to crash MATLAB before he crashes the entire computer. Thank you. So if you say 2 directly, I think he will survive, but rather violently, and he will never find a solution. So 2 or 2.001, he will blow up. You don't get a solution. So omega must be smaller than 2. To find the best omega, you have a lot of mathematical theory, numerical theory if you want, but I prefer just to try and fail with some numbers. You can find a good omega fairly quick, and here close to 2 was a good idea. So it's sort of, you take the rug and you really shake it hard, and then you find a solution much, much faster. There you have it, and it's a decent solution. So this is the successive over-relaxation method. If, as I said to you, you used what was called Jacobi iteration. What was the difference? Gauss-Seidel, you use the values that you have just updated as soon as you have them. if you use Jacobi, then you are just allowed to use old values in the right hand side of your equation system. So if we do that, then I have to reprogram my script here. Here you see I update in my matrix T, I update the values during the calculation for I, for all i's and for all j's. So here this is programmed as Gauss-Seidel. If we want to do it as Jacobi, then I have to call this something else. Call it an NT, and then also U must be N. So I have to create a separate storage, and then finally here in the end I can update everything. Now it is programmed as Jacobi. Everything is old on the right hand side. We start with omega of 1. And omega 1 extremely slow. It's going to take forever to find a solution. He's even slower than the Gauss-Seidel. So clearly bigger omega should be a good idea. But now let's try 1.01. Maybe he survives. Yeah, actually he survived. Anyway, that's not much improvement. So let's try 1.1 then. And he blows up. So Jacobi, no, you can't use it if you are going to use an over-relaxation. If you're going to use an omega bigger than 1, you have to use Gauss-Seidel iteration, or else, as you see, he blows up. How long should you iterate until you have a solution? When are you satisfied? Well, that's a little bit up to you. Let's see. So here the solution just runs and runs and runs. You can hardly see any difference. The anode gets down and down and down, and here you can continue until you go bananas. Why should you? I mean, you can't even see the difference. Furthermore, remember the problem at hand. We are actually trying to solve this equation here, double derivative equal to 0. We have used finite differences, so we have a discrete representation of the real partial differential equation with some arrows in it already. And the arrow is of second order, so meaning it's a delta x square. That's the type of the arrow. So yes, you can solve this equation system all the way down to machine accuracy if you like, but why waste time? It's a lot of arrows there already. So you should definitely stop before you just burn up your CPU unnecessarily. So when will you be happy? Well, we need a criteria here, of course. For this equation, for this problem, not so easy to find a criteria. You have the residual, as we call it, the anode, that we know should be 0. Yeah, at all points. So when the accumulated sum is very close to 0, you can be happy. That's one way to stop it. Or if we now jump back to this Sula algorithm, where we haven't gone through every details yet, it will be more next time, but here we actually have an SOR iteration, updating the pressure and the velocities. And this is actually an SOR, successive over relaxation, with a fairly okay omega. And what also we have calculated here is the divergence. And this is something neat. You calculate the divergence of the velocity field. Because here we know this divergence has to be 0 if it's to be an incompressible flow, as it should. So in this algorithm, we can actually monitor for every iteration what is the divergence now, what's the maximum divergence. And if it's too big, different from 0, then we must iterate further. We need a more accurate solution. But then at least we have a physical argument when we should stop. So when you are running this SOLA algorithm, I think the default, I can stop it here. Initially, he starts then with here 128 iterations for inside one single time step. Remember, he has to solve the Poisson equation for every time step, more or less accurate. And 128 iteration, that's well, quite a lot actually, so it takes a long time. But then, when times go and the flow sort of starts to develop, then it will be smaller and smaller changes for each time step. Then you don't need that many pressure iterations for having the correct solution or the correct time development. So just to show you, if you have forgotten what this SOLA problem was, it was then not this temperature problem, it was a square cavity test case. So 3 walls standing still, top wall starts to move at constant velocity at time equals 0, and then we will get one big primary vortex inside our cavity and some secondary vortices as well. Let's see if we can get him now. Here we have the streamlines and the stream function close to 0.1 in the center now. One big vortex, secondary vortex, and we even have pressure, and we also have the velocity contour. So this is the square cavity. Okay, now at least you have seen how to solve an elliptic equation numerically, and how the same recipe then is actually programmed inside this SOLA code that you have been given. It's not so easy to see in this source code that this actually is a successive over relaxation, but believe me, it is. It's a little compactly programmed here. You can also see here you will have this omega. The value for the omega is interpolated depending on how many unknowns you choose to use. Here I have a 20 by 20, so then an omega should be roughly around 1.86 here. So he will automatically find a reasonably good omega. There exists numerical theory how to find the optimum omega, but I find that one rather boring. Let's see, the omega 1.92 for this case. Okay, we will continue with the theory behind this SOLA code tomorrow, isn't it? We have the next lecture. Yeah, tomorrow, 15 to 17 in K number 5, just across the street. Any questions? No?